Well, if you remember, in the last class we briefly discussed about the issue of designing signals, okay, because prior to that we were dealing with uh, binary sequences or non-binary sequences in general, and we discussed information, etc. But if you look at the block diagram, after all this analog to digital conversion, source coding, possible channel coding, multiplexing, etc., this sequence is fed to a block which we broadly named as some baseband signal processing unit or something. So that's where we have to now bother about the signal features, okay, of whatever we are going to transmit, and we can consider that we have some information sequence or digital sequence at its input, okay. And towards that we discussed briefly about some features of signal, and we also decided about some simplifying assumptions, simplifying to the extent that most of the modulation schemes, etc., that we will discuss will be based on these assumptions, though there are other modulations, advanced modulation schemes for which a different set of assumptions may be necessary. Like for example, if you remember, we said that the input bits in a simplified case of binary bit stream coming into the input of this baseband signal processing unit, the input bit stream will consist of ones and zeros randomly, okay. That we have emphasized over and over again, and we assume that this probability of 1 and probability of 0 in this sequence is going to be the same, 0.5. There was some doubt why it should be, etc., but I said that after all this source coding operation, redundancy removal operation, and then error control coding, etc., over a long period of observation, if you really see the ones and zeros, they are equally likely. If they are not, in some cases, another additional operation of scrambling is usually performed to break long sequences of ones and zeros, which we have not discussed really. But on the whole, we can very safely assume that at the input to this baseband signal processing unit, ones and zeros are equally probable. Okay. That was one assumption. The second assumption was that we will now talk about some symbol, okay, signal or information carrying symbol, so to say, which again in a simplest case for a binary sequence may be that a 1 is being defined as a symbol or a 0 is being defined as another symbol. So that we can say that this incoming information binary sequence consists of two symbols, ones and zeros, okay, and they need to be represented by appropriate signals. That is the issue, okay. So we also talked about some symbol interval or symbol duration, TS in general, or T, okay. In our discussion today, we will use a symbol notation of T to indicate the symbol duration, which simply means that if I again consider a binary sequence, duration of 1 is one symbol duration, duration of 0 is another symbol duration, and there again usually, unless there is any special reason really, this duration of 1 and duration of 0, they are equal, the same symbol duration, okay. So we will also assume that the symbol duration is the same for each symbol, okay. Then the next issue is, which I did not discuss and which we will now highlight more and more, is that for we will try to find out some appropriate signal shape for one symbol of 1, another appropriate symbol shape for another possible symbol information bit of 0 shape. So in a modulation scheme, it may be so needed that 1 will modulate a carrier, okay, and 0 will modulate the same carrier in a different manner. So we need to design two appropriate signals from this binary or logical ones and zeros. That is the core issue, which is the topic of today's and maybe the next class's discussion. Okay. Now we can say that this kind of signal, the one that I am talking about, they are essentially energy signals. I hope you remember the difference between an energy signal and a power signal, is it? Okay, energy signal essentially is a time limited signal. So is the case here. I am talking about a signal which will exist over a duration of t, the symbol duration. So it's a time limited signal which we are looking for appropriate one, okay, and hence it is essentially an energy signal. Okay. Now we start about this very famous and very important procedure which is known as Gram-Schmidt orthogonalization procedure. Okay. This procedure gives us a lot of insight about how a modulation scheme can be designed and what is going to be the generic structure for the corresponding demodulator even to a good extent. Okay. It will also lead us to a very appropriate, a very nice representation of these signals which actually represent some information bits or symbols, group of bits. Okay. Now, this orthogonalization procedure says that any set of m energy signals, finite set of energy signals representing by SIT can be expressed as linear combinations of n orthonormal basis functions where n is less than equal to m. Okay. Energy signals we understand. Okay. So, it says that any given set of m energy signals can be expressed as linear combinations of n orthonormal basis functions. We are going to define, I mean, what is an orthonormal function. I guess you know what is an orthogonal function. Okay. You say two functions are orthogonal when yes, inner product is 1. Okay. Is there any sense of any duration of the signal, especially if we talk about signal now, which is a time varying is 0, then you say that the signals are orthogonal. Okay. Any other view? What? Autocorrelation is 0, is it? Yeah. Convolution of two functions is 0. Okay, we have not defined even a convolution operation, isn't it? Though briefly I mentioned about some convolutional code in general really. Okay, so let us follow our definition and that may help you in recollecting the proper way of defining orthogonality. Okay. So, orthonormality I will express and then basis functions. Have you come across this word of basis functions? Can we say for example, say that when we try to represent any periodic signal by its Fourier series expansion, okay, using some sinusoids and its harmonics. Okay, do we say that those sinusoids or their harmonics, they are some kind of basis functions? Okay, a scaled summation of all those basis functions lead to the somewhat haphazard looking periodic function, is it not? So, basis functions essentially mean a set of well defined functions which can be used through linear combination usually, okay, to generate some different looking waveforms. Okay. Here also the same meaning is conveyed really. So, what we this procedure says is that m energy signals can be represented or expressed as linear combination with appropriate scaling. There will be some scaling constants of certain orthonormal. Orthonormality is a special condition of orthogonality basis functions. The point is that the number of such orthonormal basis functions which is needed is less than or equal to the number of energy signals. Okay. Now, one can give a twist to this expression. One can say that if I have n orthonormal basis functions, okay, then I can create more number of energy signals if necessary. The other way of looking at it. Okay. If I have appropriate number of orthonormal basis functions, I can add them with scaling etc., to generate good number of energy signals, at least the same number of energy signals as the number of basis functions or more even. Okay. Let us try to understand it properly. So, if S1t, S2t, SMT are these energy signals, okay, and we will consider real valued energy signals, okay, so that we can visualize it better, we can expect to see it someday, we can expect to generate it very easily. So, if these are the real valued energy signals, each of duration t second, I am considering that the duration of each of this energy signal, because they are all energy signals, they are time limited, okay, and I am considering that the time duration of each of them is same t second. You need not worry much, even if say one of these signals, say S1t, does not exist up to t, it does not matter, it may be 0. S1t may exist for only a part of t, but for the remaining period if it is 0, it is fine really. So, t is chosen appropriately such that the signals are all defined within that interval t. Okay. Then this orthogonalization procedure says in a mathematical form that SIT can be expressed in this form. SIT is the sum of phi j_t with some scaling coefficients Sij phi j_t, j varying from 1 to n. Okay. And this is valid for small t between 0 and capital T, and I running from 1 to capital M, where capital M, as I noted, is greater than equal to n. Phi j_t's are those orthonormal basis functions. So, phi j_t's are the basis functions, okay. They are functions of time over the same interval 0 to t, okay. Sij's are constants. Sij is this, the second expression is the integration of SIT and phi j_t over 0 to t. So, these Sij's are constant coefficients. So, this is a restatement of the earlier text on Schmidt orthogonalization procedure. Is that okay? These phi j_t's, the basis functions, they are also real valued. The real valued basis functions phi j_t's, they are orthonormal by definition, okay, and this is the condition for orthonormality. Integration of phi I t and phi j_t over that interval of 0 to t. If it is 1, then it will be 1 when I is equal to j. That means, I am essentially integrating phi I t into phi I t dt, that is phi I square t over 0 to t, then the outcome has to be 1. Otherwise, if I is not equal to j, the resultant is 0. Okay. This is a somewhat special case of general orthogonality property, where this integration for I equal to j need not be 1 and it may be some constant k. The general condition for orthogonality is that integration of phi I t into phi j_t dt over 0 to t is k, some constant for I equal to j, and is 0 for I not equal to j. Yeah. For a given set of orthogonal functions, is it necessary that for any combination of I j where I is equal to, and for any given function, this k is fixed? Suppose f1t into f2t is k1, that is k1, right? F2t is f2t, that integral is k2. Is it necessary that k1 equals to k2? Not necessary. not necessary in general. Okay. For orthonormality, it is very much necessary that every time if I is equal to j, the value is 1, and there is a special reason, I mean, where in our statement when we are looking for signals, not a general mathematical function, we are choosing these basis functions to be orthonormal. Can you guess why it is so? Yeah, that is it. See, when I is equal to j, this expression simply reduces to the energy of the signal, energy of the basis function. Okay, and we are in this description we are considering that the energy of the of each basis function is unity, which is a kind of normalization we can say. That means we are looking for basis functions which are orthonormal to each other, and not only that, each of them has got unity energy. Okay. So, as if their energy is normalized. This does not anyway mean that the signal that we are thinking of designing really on the basis of this basis function, they also have to have unit energy. No, not necessarily, because those Sij scaling factors are there already. But the basis functions that we are defining, okay, by definition, this is a better way of, elegant way of expression really, that they are of unit energy. Okay. So, each basis function phi j t has unit energy. Okay. And phi j t's are orthogonal to each other. Okay. Orthonormality ensures orthogonality over the interval 0 to t. It is a very subtle idea really, you should remember, because there are variations in the definition of orthogonality amongst you really, that orthogonality is defined especially for signals over a time interval, over an interval, over a period. Okay. I mean for at least for communication purposes really, whenever we say that two signals are orthogonal, you must ask over which interval. Okay. It is not necessary that the two signals which are orthogonal over certain interval have to be orthogonal over the entire interval. It is not so really, isn't it? In fact, you know very well that say a sine function and a cosine function, are they orthogonal? A sine function and a cosine function, if they are orthogonal only over precise intervals, is it not? Not arbitrarily. Okay. So, the time interval, that means the integration interval, is a very important issue here. Okay. And our interval of integration is equal to t, the time duration over which the signal exists. Now, it will be good to have some kind of pictorial description of all these mathematical expressions, because we will see subsequently that some structures of the modulator as well as the demodulator or the receiver, they come out almost naturally, I mean, from some mathematical expressions really. To start with, if I ask you to give me a sort of pictorial description of say expression 1, can you draw that? What I mean to say is that, can you show me some kind of diagram by which I can understand how SIT is obtained from Sij and phi jt? It is not difficult, simple. Set of multipliers, okay, with this multiplier, with where one multiplicand will be the basis functions, okay, and then an adder, final adder, isn't it? So, this is the diagram, is it? So, as I could see from equation 1 really, that if I have SI1, SI2, SIN and all these basis functions phi 1, phi 2, phi n, okay, then what I do is that I multiply SI1 with phi 1 t, I multiply SI2 with phi 2 t. We remember that this SI1, SI2, these are constants, time independent coefficients, okay. Okay, they are to be multiplied by phi 1, phi 1 t, phi 2 t, they are all defined over the same interval t, 0 to t, okay. So, I multiply and I go on summing it over the interval 0 to t, and I get SIT here. So, it is so simple, okay. This may be a very interesting idea really, to do a little bit of simulation. For example, someday I give you say 2, 3 or some certain number of basis functions to you, okay, and then you can choose different, because these are coefficients, you can choose some various sets of real coefficients to see what is the corresponding waveform for SITs. okay, and a particular set you may define for S1t, another set of coefficients you may define for S2t, like that. If I say that okay, I will give you two basis functions, I require 4 signals, I can ask m is 4, n is 2, it is allowed as we discussed really. So, I will give you two basis functions, I will ask for 4 signals, okay, and one way may be that I give you these coefficients so that you find out these signals, or I give you the signals, you may have to come out with the corresponding coefficients, either way, okay. So, that is very much possible really. This also shows that I mean the selection of these signals, it need not be very restricted really, okay. In fact, this orthogonalization procedure at least is going to tell us perhaps that okay, many signals may be generated depending on these coefficients and the basis functions which may be chosen, and the actual signal shape that you are going to select from say a library of this kind of possible signals may be dependent on some other additional criteria like bandwidth and other issues, okay. But this is a very general procedure for generating various signals, okay. So, this was the depiction of equation 1. Can you do a similar thing for the second expression where we found these coefficients Sij's? It's very much possible, isn't it? What will it need? Guess. Multiplier and an integrator. Good. Is this diagram okay? There may be some problem. Just check. It's okay, perhaps. Hmm?
So we can directly have an adder and then integrate all together.
Look at this expression. No. Okay. Sij is dependent on Sit first of all and all the basis functions, isn't it? Sij is very much dependent on Sit from expression 2. So, for each I we have to have this kind of structure, similar structure. So, to get for I equal to 1, okay, by this structure we can get S11, S12, S13 up to S1n. Okay. Yeah. I'll tell you. So, you have to tell me whether this structure really I mean follows expression 2, okay, and given Sit for a particular value of I and knowing the basis functions, I can find the corresponding coefficients, the scalars, they are also called scalars. Okay. For S2t, a similar structure.
What is the significance of integrator which are integrating just from 0 to time duration?
What is it?
What's the how we say it's typically that it integrates from 0 to t or t?
How we implement it?
Yes.
Huh? How we implement it? Yeah, that's a good question. How we implement such an integrator? But we'll get back to this issue in more detail when we discuss about receiver. But yes, can anybody suggest something? Yeah, yeah, yeah. Well, in many cases, I mean, we draw some kind of equivalence between this integrator and a filter. But I mean, trying to answer his question really, can we really integrate this even without using a filter really? Hmm. Hmm. Pardon? Huh. Right. No, 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 no. I mean, my suggestion at the moment is that don't get into any equivalence really. Let us try to see directly whether I can implement such an integrator. Towards that, I mean, tell me, I mean, if I can implement an integrator at all by using electronic circuitries, yeah, fairly well. Why not? Huh? Only problem then is, I mean, how to integrate only up to t,
We can have a clock
and then
a switch which will put the input to 0 at
input or output.
The input to the integrator would be 0 after time duration t.
That's it, isn't it? So what we need is an integrator, okay, whose input as well as output, we'll see later, okay, can be switched, can be bypassed, can be grounded to 0.
But even sir, while dealing with the integrators which we do in the lab, like to maintain the integrator output.
In a lab, you always fall back on simple RC integrator even without using an op amp really. Okay, if you use an op amp, you get a much greater integrator, much better integrator really. It charges at the constant rate. I mean, I is a constant
But like
rate.
if we stop the input to it, it will fall down.
Pardon?
It will fall down. The
Huh.
output will fall down.
So now then that leads to the next question really. See, I mean, this is a very interesting issue and is a core issue in the design of what is known as a matched filter receiver. We'll discuss about that later really. This integrator, I mean, in an appropriate form is known as integrate and dump circuit. That means the input, whatever is coming, okay, will be available from 0 to t. One question is what happens after t? We'll see that.
you charge a capacitor and then
No, I am not talking about the integrator behavior. I am first trying to understand. See, if I take out this integrator separately, this discussion is going to be relevant. Okay, so we may spend some time on this. See, let me take out this integrator. His question was, I mean, how do we implement this kind of circuitry? And his worry was uh, uh, because we are integrating only up to t. Okay, so towards that, gradually, let me just think about what kind of signal change we are expecting at the input of this kind of integrator, and where. Is it that, for example, let us just consider that this structure is good for generating for I equal to 1 S1t. Okay, but suppose you also would like to know all other scalars for other values of I. Okay, so you may have a plan that you will feed S1t here for a duration t, you will feed S1t, and then in the same structure you will feed S2t for the next duration of t, and then S3t. Is it not that the same circuit will give you S11, then S21, then S31? So by using the same hardware, by feeding S1t first, then S2t, you can find out all the scalars.
We need to reset the integrator.
Yeah. So what you can say is that this input may also change after t, after the interval of t really. Okay. So the input may change after t. Okay, but every time the integrator has to integrate, so the integrator must start from initial condition. There is no constant value here really, which means before the integration is ready for taking the next set of input, next signal over the next interval of t to t, so to say really, then it must be initialized. So there is not only a requirement of integrating up to t, there is also a hidden requirement of initialization before it can accept the next set of input. This is some summary for the input to the integrator. What about the output? What we are going to do with these outputs really? At this moment, we are trying to find out the coefficients, scalar coefficients. So after we have found these coefficients, because they are coefficients, because they are constant, the value is obtained at t equal to capital T. Is it not? So I store this value, I take out this value, okay, so that I can take the next set of scalars between t and capital 2t. So at t equal to capital 2t, I can get the next set of scalars. So the output I will take out and make this output line free. Okay, so a good approach may be in general to design this circuitry such that it integrates over a duration of t, then the output is held for some time so that the output can be taken out. Okay, then the integrator output is dumped or initialized to 0, so that now the input gate is opened to accept the next signal. Is it not? If I do this kind of circuitry around this integrator, simple integrator, then the same hardware structure can be used conveniently for not only seeing one S1t really, I can set any set, any signals SIT, any value really, I equal to 1, I equal to 3, any for any value of I, is it not? So, with that kind of structure, we call this circuitry as integrate and dump circuit. Okay. This integrator will have some kind of output bypassing arrangement, okay, and the output will be held before that for some time, so that the output can be sampled by the subsequent circuitry, and then the output will be dumped, so that the circuit is initialized and is ready to accept the next signal. Okay, we will have a more appropriate description of this circuitry when we discuss about matched filter receiver, okay, with integrator and dump circuit. But this now has brought us to a good point, really very interesting point, is that once you have understood this diagram, now think a little bit. If I say that my basic transmission problem is, without talking about carrier at the moment, my basic transmission problem is that I have a sequence of ones and zeros, which I am now preparing myself to convert into a set of signals called S1t, S2t, etc. And as if ultimately I shall transmit these S1t, S2t's only. Of course, many cases using some carrier, but that is not very important. At the receiver, if I get these S1t, S2t, etc., from that I would like to get what I have got exactly, whether it is really S1t or S2t, because if it is S1t, I know how I generated S1t at the modulator. Maybe 1 was represented by S1t. So, if I can recognize S1t at the receiver, I will say 1 was transmitted. Is that okay? Okay. Consider that I had two signals S1t and S2t. S1t is representing 1, logic 1, S2t is representing logic 0. So, in the modulator section, in the transmitter section, I will generate S1t or S2t depending on whether the information bit is 1 or 0, and I will transmit S1t and S2t. Okay. At the receiver, I will observe over a duration of t and see what I have got. Is it S1t? If it is S1t, then I will say 1 was transmitted. If it is S2t, I will say 0 was transmitted. How about this scheme? Should be fine. Only thing is that, I mean, at the receiver, we will be observing over a duration, and this duration is symbol duration. We will observe over this symbol duration, but the point is that we do not expect to receive S1t cleanly, isn't it? Because during transmission many things happen, we already know. There will be noise, there will be other kind of problems, interference, etc. But whatever it is, those are subsequent issues. But the fundamental issue is that SITs can be transmitted, okay? And at the receiver, in a very general form, we would expect, one strategy will be to observe the received signal over a duration 0 to t, the symbol duration, and from there appropriately try to decide whether it is S1t or S2t. If this decision is good or better, then your receiver strategy or reception scheme or demodulation strategy, it comes in various names really, that is better. We will try to see, I mean, how we can design a best receiver and other issues subsequently, but this is a starting point towards that. Okay. With this in mind, now tell me, I showed two diagrams, isn't it? This one as 1 and this one as the earlier one, equation 1. Try to guess where this diagram should fit in the transmitter or in the receiver. That is right, isn't it? Okay. So, this diagram should fit into the transmitter, and this diagram, is it not? Huh? Because then in the transmitter, which where the purpose is to generate a signal after receiving some information bits, what I will do is that I will store or I will generate from some circuitry, okay, S1 corresponding S11, S12, S1n, when I have to generate S1t, and if I have to generate S2t for 0, I will generate S21, S22, S2n, and I will get the corresponding S2t, I will transmit this signal.
This is the way tone dialing works, something like that.
First of all, tone dialing is not a form of modulation scheme really. I mean, what it does is, you dial in a key, okay, and it follows a matrix structure really. It depending on the key you have pressed, it generates certain tones for some duration, okay, fine. And now these tones, there are several tones really. These tone combinations specific, I mean very uniquely identifies the key that you have pressed. Okay. Let me try to understand his question. I mean, in a tone dialing system, when you press a key, what key you have pressed must be understood at a somewhat distant place, and for that, when you press a key, two frequencies are generated. Okay, these two frequencies are detected at the other end. Okay, and from that one can identify which key was pressed. It is a form of frequency generation, tone generation scheme, of course. Okay, but that's not the usual modulation demodulation scheme really. I mean, there the issue is to identify the frequency tones only. Okay, no, and only that frequency values, they convey the information that which key has been pressed. Fine. Now, in this general modulation demodulation scheme, we will be talking about a more diverse situation, where I mean we may not only transmit some tones.
But sir, in the telephone communication, if you have to use tones only as a means of frequency, the main carrier is the frequency itself.
No, in fact, these
like
tones.
modem uses.
Right.
They also generate like particular binary number is converted to a frequency format and then it is sent.
No, it is like that. When you talk about tone generation for dialing really, these tones or frequencies are not carriers. Okay, for transmission. Okay, these tones, they stand for certain number, the key that you have pressed really, and that carries information, and this whole tone is to be understood at the exchange level. Okay.
But it could be like there are three frequencies and it could be some of any two of them or something for a particular number.
No, it's not. It doesn't go that way really, because if you sum them up, it leads to a lot of complications in detecting the carriers, detecting those tones. These tones are very carefully designed. The tones which have ultimately been standardized, they are very carefully designed so that the corresponding band pass filters, narrow band pass filters, they can be designed, okay, and they can pick up the corresponding tones without any false pickup, etc. The design approach is different from our design approach of modulation demodulation.
So for like different numbers, one tone at a time, or maybe for serially different combination of different tones.
No, the tones go together, but the tones, they are in different frequency bands really, so they can go together. So what is done at the other end is narrow band pass filters are there, so the tones pass through them. Only from two band pass filter output you get high output.
Basically addition of the two tones. If you are sending two tones.
Oh, addition means in the time.
Yeah.
Oh yeah, that's there, but it's not that two frequencies are added. It's not that way. Sorry, I mistook that as a frequency addition. It's not that way. The simple tones, they are generated simultaneously and they go together. Okay, they get multiplied. I mean, they get added in time. That doesn't create a problem because you have got narrow band pass filters to separate them out. Okay, the situation he was talking about is not the one that we are visualizing here. The issue is ultimately that of transmission and reception over a large distance, and during this process of transmission there will be noise and other effect, and the focus is going to be more and more on the receiver structure design. What kind of receiver should be designed such that we can detect the signals, we can detect the information bits without any error or the minimum amount of error. That is the issue. Okay. So, rightly this kind of structure can be followed in general in the transmitter, or I can say this is perhaps a kind of modulator which is going to emerge subsequently if you are convinced about this orthogonalization procedure. And then this diagram may fit in the receiver, okay, where in a general form I may get some kind of RIT instead of SIT. Maybe SIT was transmitted, S1T was transmitted, but what we may receive here may be R1T, a bit different from S1T, different because of noise, interference and other problems. Okay. And then what we will do is that we will use these basis functions, we will integrate them, we will see the output at t equal to capital T, okay, and then from this set of scalars we can now try to guess whether R1T is closest to S1T or R1T was closest to S2T. Does that make sense? See, this set of scalar is unique for S1T. For S2T, there will be another set of scalars. So, from this set of n outputs, if I now try to find this set is closest to S1T or S2T, I can perhaps take a decision here whether S1T was actually transmitted, which was received as R1T. So, this structure perhaps is going to form a part of the receiver or demodulator structure. Okay. In fact, we will see an optimum demodulator, which is known as maximum likelihood demodulator or decoder, also some cases maximum likelihood demodulator.
Narrowband pass filter, just like a multiplier.
Which one? Which one?
Like the 5-1T, your SIT to 5-1T, you are basically extracting the particular, you are demodulating in the sense.
We are demodulating. This is.
This could be also done in the same way by narrowband class systems. If we really know what's 5-1T corresponding.
5-1T, these basis functions are known. It is assumed. So they are known. I mean, what would be the feature of that filter? Can you guess?
Like the 5-1T is a carrier.
No, I have not said that. Did I say that 5-1T is a carrier? It may be. It may be, but it need not be in general. It need not be in general. Okay. In fact, that's why I was saying that. I mean, the carrier part is there. Okay. We'll talk about that sometime later, but it is not essential to always think in terms of carrier. In fact, what I shall try to do is we shall try to describe this process of transmission through signal design without carrier. Okay. And we'll see that the approach remains the same whether there is a carrier or not. If there is a carrier, these basis functions may look different. One may define basis functions using carriers. One may also define basis functions at the baseband level without carrier. Okay, we'll try to understand the baseband signal design first. So our basis functions are baseband signals. It is not carrier related at the moment. Okay. Sorry. So this structure finds use in the receiver. That is a major part of the receiver is made of this kind of structure, and there this special structure of a multiplier with a known function and an integrator is called as a correlator. That means this structure, if you see closely, what it does essentially is it tries to correlate if the incoming signal is at all related to phi 1t. If S1T has got something related to phi 1t, that will stand out here. And if I go back to our expressions, we will see that that is what is SI1. So, this structure of a product multiplier, okay, and followed by an integrator over a certain time is also known as a correlator structure. So that we can say that this kind of structure is nothing but a bank of correlators. A bank of correlators is used where the input signal is fed to each arm and we get some scalars at the output. Okay. This is a major part of the receiver scheme which we will study later. Okay. No, this is a constant. This is a constant coefficient. Okay, so it has to be some voltage level, voltage or current equivalently. Okay, some signal. Because what I do is that this integrator integrates at t equal to capital T. I just sample out what is that value. Bas. Well, we'll start some justification about this Gram-Schmidt orthogonalization procedure. Okay, maybe we continue the next day. We'll try to justify this. Yes, this is indeed the case that we can represent m energy signals by n orthonormal basis functions where n is less than equal to m. Okay. For convenience in understanding, we try to justify in two parts. In the first part, what we do is that we try to show that a given set of energy signals, m energy signals, it can be described, all these energy signals can be described by a subset of this set energy signals whose elements are linearly independent. See, our Gram-Schmidt orthogonalization procedure says that any given set of m energy signals can be represented as a linear combination of n orthonormal basis functions where n is less than equal to m. So, with some twist we are trying to justify it in a somewhat indirect manner. what we are trying to establish first in the first part of the justification is that if m energy signals are given, then these m energy signals can be represented by a few number of energy signals chosen from this set which are independent of each other. So, you give me a set of 10 energy signals, I should be able to represent these 10 energy signals by 2, 3, 4, 7, 8 number of independent energy signals drawn from that set. This is possible, and I mean strikingly very simply, I mean it is not very difficult to establish this. So, if m energy signals are given, it means that it is possible to find some energy signals from this set which are independent of each other, and then the remaining energy signals which are not independent of each other, they can be constructed by a linear combination of these independent energy signals. One point to be noted here is that in this part we are not talking about any orthonormal basis function so far. We will talk about that in the second part of the justification. So, we are starting with the given m energy signals, okay, and I am trying to establish simply that from these m energy signals we can ultimately get some of these energy signals, some members of this set which are independent, and I can again use them through linear combination to get all the, to express or represent all these remaining energy signals. Okay, that is the point we are trying to establish. So, to start with, we assume that all SITs are not linearly independent. Okay, the energy sets that you have given me, m energy signals, one possibility is that they are all dependent. Okay, the other case is that I mean they are all independent. That means m energy signals are all independent. What does it mean? That any but n equal to m, yeah, I cannot represent any of these energy signals as a linear combination of the remaining energy signals where the coefficient of multiplication will be non-zero. I can do that. Okay. So, that is one case which does not require any discussion, as you have rightly said, which means that m is equal to n. Okay. All these energy signals are independent already, but this need not be the case in general. So, I am considering that they are not all of them are independent. So, some of them are dependent. So, what I do is that we can always think of a set of coefficients ai's, okay, m coefficients I varying from 1 to m, not all of which are 0, all of them should not be 0 simultaneously, such that this identity is valid. Because all SIs are not independent, I can write this expression. Are you convinced? If all these energy signals SITs were independent, then I could not write this expression unless all AIs were 0. But because there is some dependence, okay, it is possible to find these coefficients AIs by some method, by some computer search or otherwise, such that this identity would be true. In fact, the basic essence of dependence is incorporated in this identity, okay, where these AIs can be searched out by some means. Then arbitrarily, without losing any special feature really, we are assuming for the sake of notation only, okay, I am assuming that m is not equal to 0, okay, at least one of them has to be not equal to 0, okay, because there is some dependence. So, if I assume that m is not equal to 0, then it is simple to show that SMT, the mth energy signal, actually is dependent on the all other energy signals in this form. Expression 5, SMT can be from this identity can be expressed as minus 1 upon m summation AIT AI SIT. AI are, these are constants really. Is it okay? Now tell me, if SMT, when SMT will be dependent on all of SITs I equal to 1 to m minus 1. See, this expression simply establishes that the mth energy signal is dependent on others. Okay, how is SMT dependent on all others? That depends on the values of these coefficients. If all of them are non-zero, then yes, SMT, the mth signal depends on all other signals. Okay, but that's not the point at the moment. At the moment, we have established that if SMT is a signal which is dependent on others, then SMT can be expressed like this. Okay. So, yeah, so we stop here basically. So we could see that from equation 5 that SMT could be expressed as a linear combination of other SITs. Okay, so we leave out SMT. Then we will start from this point. We consider a smaller subset of energy signals with I varying from 1 to m minus 1 this time, leaving the mth energy signal, because that has been found to be dependent on others. We are gradually trying to show that all these dependent energy signals can be eliminated, and ultimately we will have a smaller subset of independent energy signals. Okay, so we'll has to be less than n, because if there is dependence, that we are now assuming that there is some dependence, so we have got SMT. Okay, so we have left it out. So n is now less than equal to m, less than m. N will be equal to m when all the signals are so given that they are already independent. Then n is equal to m. Yeah. Okay, but they need not be same as the basis functions, because the basis functions are special functions which are orthonormal. They are orthonormal with unit energy. Yeah, some kind of scale version of that. Okay, so we stop here today, unless you have some question, and we continue from this point in the next class. Okay, thank you.